Let me just introduce Odin properly, but promise me it's the last time because, well, I've introduced Odin so many times in life that, I no longer know how to do it. And I'm officially running out of ideas. So officially, Odin was allocated to us from a pool of hippies in the middle of a forest. And he spent most of his career designing electronic circuits and programming microcontrollers in assembler. One day, after Odin shot himself in the foot, there was a friend, and he introduced him to C++, and then in Odin, a serious addiction followed. And so Odin has authored many proof of concept libraries in the embedded field and is trying to revolutionize this domain. And in his day job, he, of course, teaches people how to shoot themselves in the foot less, and at the same time get more from their compiler. And he does that both with his in-house team and in training as a consultant. And today it is called What I Wish They Told Me, and this is part 1 of 2. Odin Holmes.
Thanks, everyone. Thanks for talking up my work ethic. That's actually going to be part of the talk. This is a different talk than I've usually done. Most of my talks so far, or all of my talks so far, have been very high-level sort of expert talks on one topic or another. And I've noticed throughout sort of the last few years of my career when I've been going into other companies and talking to people who work in other workplaces and not just my team, that the thing that I've noticed about myself is also true of other people. Most times that you screw up, it's not something very high level that you didn't understand. It's something very low level, something very basic, which didn't allow you to propagate some piece of knowledge all the way up the chain, so that there's a branch in your tree of knowledge which is half-truths, right? And the problem is you don't know where these are, right? And so at the very, very high level, most of the stuff I've been doing, one could probably arrive at oneself if one had sort of a perfectly cleaned and defragmented tree of knowledge below that, right? So it's not that impressive. This is the first time I've been doing one of these sort of advice talks or beginner talks, or, another alternative title for this talk might have been My Existential Crises, and So Can You. Yeah, this is sort of advice that I would have liked to give my former self, or advice that I hope to give to some of you so that you don't shoot yourselves in the foot as much as I have. Because I didn't start as Odin the Nerd. I actually started out as Odin the Hippie. Oops, my clicker's not working. There we go. Odin the Hippie. Notice that my jacket is very dirty and no one cares. This was a school photo. Yeah, I actually do come from the middle of the forest in a hippie commune of like 8 or 9 families that were school friends before the Vietnam War, and then all hid from military service and then joined each other in the middle of nowhere in Oregon. And it's a little lonely being the only nerd in a bunch of, in a hippie commune. And this sort of gave me sort of a predisposition of, not seeking outside advice and just trying to figure out everything myself. And I was actually pretty good at it, I guess in some sense of the word. I founded a company making electronic circuits for vehicle diagnostics. And the thing you need to know about electronics, if you have sort of a very sort of high view of electronic engineers, that's true for some of them. For most of them, it's very similar to software, where if you read the manual and use some good library, some other people have already done all the work, right? This is from Texas Instruments. It's how to make an ECG machine. And all of those components have numbers. If you connect them in this way and use all those components, you'll probably have a somewhat functioning ECG machine. You don't have to know what you're doing, as in software. Okay, you'd need a power supply, so let's make one of those. Some other company, some other thing, and this power supply probably has way too much ripple for that, but we don't care, right? It'll kind of work. Maybe it'll blow up, and if it does, we don't understand why, right? And this is there's evidence of this throughout, the products of these electronic engineering. If you look at very expensive laptops from fruit companies, there's some capacitor problem in the power supply that's been there for like 8 years, and I believe at least either in the data sheet or in basic electronic engineering courses, they teach you to not use that kind of capacitor for that job. But, maybe not the best engineers in the world, but probably the most expensive, seem to not know that. Right? This is a very, very, very basic. I'm sure they have a lot of expert knowledge on top of that. I mean, sincerely, I believe they have a lot of expert knowledge on top of that. But the fundamentals are kind of somehow missing. Right? And that was sort of a place where I was. I had products in the field. I was earning money. I was young. I started my company at 18, and it was still in my living room. But things were good, and I was programming an assembler because every electronic circuit today has a microcontroller in it, and this is actually some of my code from back then, and I started programming assembler without having any, formal software training or any other languages influencing me before that. So there's actually a few pearls in here. We might get into a few more of them later, but notice after a call, a call in assembler is basically take this address, push it to some stack, and then jump there. No stack frame making, none of that. Just jump somewhere and remember where you were. And after every one of these calls, there's an unconditional branch to an error handler. I mean, this is something like boost outcome in assembler, right? It's a discriminant union of either an error or the result, and the discriminator is, I just manipulated the address that you returned to, right? So you call the function from one address, and then if it's a success, you will return to one address further, or 2 addresses further, as it were. You won't return here. You won't return here to the error. If you call this, you will return here if it's a success, right? And I would certainly not suggest doing this on any modern architecture because you will completely confuse any branch prediction. And your program will run incredibly slow, but this was a microcontroller that had something like 500 bytes of RAM. And it was not that sophisticated, so this was actually a very pragmatic, very good solution for this problem. And sort of in my little view of the world, optimizing assembler and getting better at writing assembler seemed like the way to go, because and if whoever's programmed an assembler on bare metal without an operating system, show of hands. Okay, a few guys. You have to lay out your own memory, right? You don't have a linker that does it for you, right? So you basically have this address space, and you keep track of what goes where, right? And that actually requires a lot of discipline. And you can muster a lot of discipline. I would argue you can never muster infinite discipline, right? And there were sometimes bugs that would take me days to find, right? Because the debugger was not so good either, right? And so I got very frustrated in my sort of assembler writing life, because no matter how much more disciplined I was, I still didn't achieve complete bug-free code, and it just wasn't quite working the way it should, right? And I mean, it worked well enough. We were we ended up being the most sold diagnostic product in the world, but it didn't work as well as it should have, right? I mean, there's always room to achieve better sort of robustness and less errors and so on and so forth. And okay, so you could say maybe I'm not a very good measure for how disciplined someone can be. And this assembler program I wrote was something like 8x smaller than the Apollo guidance system. That's the Apollo guidance system printed out next to the head engineer, Margaret Hamilton. And she's apparently much better at being disciplined than I am because the Apollo didn't crash. But if we think about sort of increases in discipline over time, right? And Exhibit A, not discipline, right? I didn't label these axes, right? Not very disciplined, right? So let's assume, okay, this is effort, and this is amount of complexity that one can deal with because one is very disciplined, right? So the more effort you put in, the more complexity you can manage, right? If we say, okay, maybe I'm more towards the bottom of this scale, just for the sake of argument, other people are better than me, and then maybe we have some outliers, and for the outliers, we must use the unicorn pen. Well, Margaret Hamilton's probably one of these outliers, right? But this is a law of diminishing returns problem here, right? I mean, the more effort you put in, the closer you get to some boundary line, but you never cross it, right? And the problem is that the level of complexity of a lot of the world's problems is maybe on the roof of this building several floors up, right? So, if we look at, we can make many of these sort of law of diminishing returns things. Maybe we have a larger project, and the more time we get, the closer we get to finishing it, with less and less return on that investment in time, right? I mean, as from a programmer standpoint, one usually says, okay, if we'd only had a little more time, there would have been less bugs in the program. And that's probably true, but to an ever diminishing level. Maybe if we had more programmers on the team, maybe we would have gotten there faster, or maybe not. Maybe we should rename these axes adding people and productivity, right? I think the joke I overheard yesterday at dinner was, if you need to explain this to your boss, buy him 3 copies of the Mystical Man Month, because then he can read it 3 times faster. So programmer discipline, infinite programmer discipline, is a unicorn. Some people believe they exist. Some people believe they live in the forest, and we just haven't seen one yet. But I believe that unicorns don't live in the forest. So, I mean, the problem is, if you're in this sort of situation where you're fighting a law of diminishing returns, I mean, this is kind of, in my opinion, how people burn out, right? It's not really about man hours. I mean, I know a lot of people that work insane man hours, and I know a lot of people that work in government jobs that have legally limited number of man hours, something like 35 a week or something, which is just, not a lot. And the ratio of burnout is somewhere similar, right? And, maybe if you can work more hours, that might be a symptom of getting closer to what you perceive as your own potential limit and being frustrated with this. And I was personally very, very frustrated with this because, I saw myself as somebody who was sort of tried to be useful, somebody who was good at this, and this was the thing that I was the best at in my life. And this was very hard for me, and I to sort of went to very extreme measures to try and cope with the problem that I had, which I perceived as me not being good enough at this, right? Which was true, but in a different way than I perceived at the time. And so I'd program at night because people would interrupt me less, right? I'd start programming, something like 10 o'clock in the evening when everybody left, and I'd go till 5, 6, 7 in the morning, and then I'd go to sleep and sleep all day, and then I'd program at night again. Went during crunch time when the new firmware had to go out. And that helped. I got a little higher, maybe sort of not yet approaching that unicorn line, but, but it also had terrible effects on, my personal life, my psyche and whatnot, and I'm glad I had good friends, because otherwise I think I would have seriously burnt out. at that point in my life. I had sort of weird psychological effects because apparently speech and visualizing data flowing through registers are very different things in your brain. And so if someone would call me in the morning and I'd still be up and I'd pick up the phone and I couldn't talk, right? And I'd have to wait for, they'd be like, hello, what's up? And I'm just like, okay, codec not found, right? And so I can very much understand a lot of these, young people that burn out fighting the law of diminishing returns, right? And, the problem was that sort of my electronic engineering skills were also hitting a wall. There was some of the magic smoke was coming out. I'm not sure if you guys are familiar with magic smoke theory, but during manufacturing of electronic projects, they have this big tank of magic smoke, and they inject a little bit of it into every chip. As long as that magic smoke is in there, it works. As soon as the magic smoke comes out, you can't put it back in. And luckily, sort of in my electronic engineering side of things, I had what I considered my Maxwell moment, right? Where I kind of realized there's an underlying system under all of this, right? I mean, before that, it was just a grab bag of, here's what this manufacturer wrote about this chip, and here's what this manufacturer wrote about that chip. And I couldn't really fundamentally reason about the glue in between, and I couldn't really fundamentally reason about problems for which there was no demo design. And I mean, a little, but I was often wrong and lost a lot of magic smoke. So, I, to this day, don't understand enough math to actually explain to you exactly how these Maxwell equations work. But sort of in my mind, in more of a sort of flowing visualized thing, I kind of understand it, right? And I would suggest that every engineer read these books, the Feynman Lecture on Physics, even if you don't understand all of it. But the takeaway here and what sort of my gut got from this book, which was very, 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 very helpful to me. And it doesn't have to be this book. It can be some other sort of grand theory of everything. But there's not that many of those that aren't crap. So, in this book, Feynman ties physics to all sorts of other disciplines. Medicine, chemistry, and, sort of this new way of thinking, not necessarily anything specific in the book, but the new way of thinking of things, of sort of looking for a deeper understanding of the fundamentals and then reasoning up from there to actually understand a lot of the things that were going wrong, a lot of the reasons for magic smoke. I mean, funny enough, to this day, whenever somebody lights up a cigarette, I think, oh my God, where's the short circuit? Right? Something hardwired in my brain. Oh my God, something's frying, because you smell that, and it just, oh. So that was, ironically, that was my first Maxwell moment. My second Maxwell moment came several years later. The first one greatly increased my productivity. The second one was the birth of my son, Maxwell. Certainly did not increase my productivity, but 10 of 10 would father again, right? So, somewhere around this point in time, when I had asked a friend to help me with one of my assembler errors, and we were kind of looking at it, and I figured it out, and then he had sort of an offhand comment of, if you'd used a real language, that wouldn't have happened, right? And that kind of stuck with me, and I figured he was right, and I looked at C, and I looked at C++. The problem there, especially with C, was I could not express myself in C in a way that would map to any kind of efficient assembler, right? I mean, this was like, 5x, 10x less efficient than the assembler that I'd been writing. Anything that I was able to write in C with sort of a, normal beginner's C capability, right? But I noticed that, in C++, at least you can start to kind of make your own rules, right? I mean, you can kind of start to combat this, so that's what I went with. And I hadn't used it on microcontrollers yet, but I was using it on a desktop machine, writing a driver This was a C++ driver. It was supposed to provide some kind of high probability hard real-time constraints. You can't do hard real-time constraints on an operating system, but if you never touch anything outside of your thread and always, always finish in one time slot and always block and wait for something where the scheduler can reason about you being blocked for that, you get a little priority boost. And so if you make sure that you're the highest priority and you always finished all your tasks within one time slot and you never touch the allocator and you never touch anything that might block with any other thread, then you can actually achieve somewhat real-time behavior as a DLL loaded in a Java program. I would not suggest being that person, but weird stuff like loading you 10 times before they unload you and loading and unloading you in different threads and all sorts of weird stuff. But I had, this was kind of the level at which I was programming C++, which in this case could have been C, right? And who here recognizes something like this from their code base? Some sort of this sort of level of, it's kind of legacy code kind of stuff, right? And there's obviously the problem of size and data being part of the same thing, right? And not being able to enforce invariance between size and data, like that size is always a smaller count than the length of the buffer in data, things like that. But actually, what broke in this particular case was the packet ID and protocol ID. In one handler of a protocol stack that happened to be protocol ID number 2, I had switched them around. And the ironic thing was, in this particular vehicle protocol, was just there to open up a channel to other control units with which one could then talk on another protocol. So packet ID 1 is I want to open a channel. Answer is packet ID 2. Says, okay, that's where the bug was. So it worked. Everything worked for weeks until somebody in China said, hey, I've got this problem. And it turns out there's actually only one control unit in the world that's not fast enough to just answer, yes, that protocol channel is open. And it says, wait a minute, I will open it in a minute. That's packet ID 2, and then comes packet ID 3, saying now it's open. And the world breaks. Right? So I had the problem of being in Germany with a relatively low budget and having a bug that only happens in China. So that took a good couple weeks of my life to figure that out. And before that, my view of good code and optimized code was, had something to do with not typing too much, right? And I came away from that situation realizing that in 3 weeks I could have physically typed the entire program, right? Typing is certainly not the bottleneck, right? And this again is, a lack in discipline, if you will, right? A lack in checking that everything's right, right? And the problem is, as complexity goes up, the amount of things that you need to check go up exponentially as well, right? And you've bought something with C++ because there's a lot of stuff that you don't have to check anymore. Can't blow a stack frame if that's encapsulated away from you. Can't misindex a pointer. Off by 1 means next object and not 1 byte into that object, right? So it bought me some sort of ability to cope with complexity. But there it is again. I'm fighting against this sort of exponential curve of everything's getting harder and I don't know how to deal with it, right? That kind of led to what I'm going to call my Alexandrescu moment, where I realized, on some fundamental level, we only really have sort of 3 things in sort of my world of programming, which, you can disagree with, but sort of the way I view the world. We have data, which is just bits and means nothing without type information. The type information is basically the bookkeeping language of the compiler where it keeps track of what your data is, right? And the type information goes away when you compile it, right? It's only sort of manifestation left is the subroutines that get called for any given conceptual task, right? If I say A plus B, that's going to be a very different string of assembler depending on what A and B are, right? So type information is also not just sort of what function gets called when I say plus, it's also what operations aren't legal, right? What can't you do? So, you know, the Alex Andrescu moment was sort of, I can offload my discipline into the compiler, right? I can have the compiler check things so I don't have to. And his book was sort of the first book, C++ book that I read cover to cover. And, you know, admittedly like 4 times before I understood it. But, yeah, sort of the takeaway here was, you know, I could very simply, you know, wrap packet ID and protocol ID, and suddenly I did not need to be as disciplined anymore, right? I'd sort of raised the level I'd sort of raised the curve of what I could achieve with the same amount of effort, right? And, you know, this doesn't necessarily have to be fancy template web programming stuff, right? I mean, making sure you don't break things could simply mean I wrap my ints just in a struct, and I do everything by hand. It's ugly, but you can't switch them around anymore, right? And it's certainly not an efficiency loss, right? I mean, if you look at the generated assembler in release mode, that's going to be the exact same thing, or less, ironically, right? I mean, in some cases, the compiler can actually reason about 2 different structs, or at least references to 2 different structs, not being the same struct, and can do better optimizations based on that knowledge, right? I mean, this was another realization that followed relatively shortly, is that close to the metal is a myth, because what is the metal, right? I mean, you can program close to an abstract machine, but if that abstract machine has been around for a while, that abstract machine is probably close to some metal that was current when I was born. We have different metal now, right? And this is kind of a you know, sort of odd advice, I guess you could say, or not typical advice on performance, but I actually spend a lot of my day job looking at generated assembler. I mean, not the level of complexity of assembler of a current core, but on simple cores, and, you know, looking at what the optimizer does, and it's very hard to reason about what the optimizer is going to do, and that's good, right? I mean, the optimizer being a lot smarter than any single one of us, because it's the sum of a lot of people's work, is a very good thing, right? So, you know, I've kind of come to understand that, you know, these people that have sort of this optimization advice, they usually don't actually look at the generated output, right? And people that do will tell you it's complicated, right? So what sort of general advice can I give you guys about my experience of, you know, writing different forms of code? Because in template metaprogramming, you can change the way the code works very easily, comparatively, because you have one point at which you change the algorithm of code gen. And looking at the resulting assembler is that you can almost assume that the optimizer will do the right thing if it is allowed to and if it can see it, right? And if it can see it depends on whether or not you're doing link time optimization or putting things in headers, right? If there's a function in a different translation unit in normal release mode, it will not see that, right? But more importantly, it cannot see through indirect calls, right? So if you have a virtual function or you have a, you know, function pointer you're chasing, chances are, the optimizer does amazing things, but in most cases it can't see through that, right? The other even more important optimization advice that I can give is that the optimizer is not allowed to rearrange your data, right? I mean, Heap allocation elision is the exception, where if you put something on the heap, sometimes under some circumstances, modern optimizers can take it and put it back on the stack. But the layout of your data types is observable at compile time, right? So you can make decisions in the compiler based on how big an object is, what's in it, where it is, and whatnot, right? And because you can do that, the optimizer can't reason about what conclusions you drew or what the results were of your reflection on that data type. Plus, there's also the whole can of worms of ABI breakage, right? ABI expects a certain layout, and your optimizer doesn't know what data structures take part in public interfaces to things that need to remain ABI stable, right? So if you have a structure that has dead data in it, as a pendant to dead code. If you have dead code, your optimizer will figure out, no one's ever calling that, gone, right? Unless somebody's taking its address, in which case it might be an indirect function call and the optimizer can't see, but if no one's ever taking address of a function, then gone, right? But data, not so much, right? It can't. It's not allowed to. And it can't reason about a lot of other things where it can't see through sort of pointers, right? The optimizers are generally bad at seeing through pointers, right? Even in the case of data, right? If I get two pointers to things and they could conceivably point to the same object, suddenly I can't reorder a bunch of stuff because it could be the same object, right? And so all of those void pointers in C don't look so efficient anymore, right? I mean, my view of what code is efficient has changed very much over the years. And there's also some sort of current research on this topic. John Rieger is doing research on, the sort of elevator pitch is formally defining what a processor is, and then running a SAT solver to figure out for common assembler patterns what the most efficient way to do that is, right? So it's not just dependent on man hours coming up with optimizations. It's becoming more and more dependent on, provided his research is a success, execution time, right? So as the abilities of optimizers is trending up, writing performant code is getting more and more to be a topic of, at least for the beginner, a topic of allowing the optimizer to see a lot of stuff, right? I mean, less virtual functions, less indirect function calls. And if you get into some niche part of the world where you want to write your own SSE instructions, then go do that, right? That's not off the table, but as sort of here's where you start, right? Ignore almost everyone, use the optimizer and let it see stuff, right? Because inside the compiler, that's where the unicorns live, right? This is, they don't live in the forest. That's where you put your discipline, right? And that will scale very well, because compilers scale. Compilers scale to an incredible degree. Right? Coming back to the question of, how do I know if my code is good, right? And this is a question that I asked myself at the beginning of my career, and I actually have the luxury of working with a lot of people who are smarter than I am, but don't know how to write software yet, right? I mean, they're very, very good physicists or electronic engineers or just generally smart. And when they ask this question, then I feel like I need to come up with a good answer, right? But this is actually a really, really, really hard thing to answer, right? I mean, code that works is good, right? Well, my DLL worked for a couple of weeks, right? I mean, how do we know if we've seen all the test cases? Right? I mean, maybe I unit test my code thoroughly, right? Well, did I unit test all the cases? And even if I did unit test all the cases, is this still not going to break in the future? I mean, what are the assumptions that I've made that will make this break in the future? I mean, if you think about my laptop, for the sake of argument, as a state machine, right? This is a state machine. How many states can this thing be in, right? And this was a very, very good question asked to me by one of my employees. Like, can't you just view all software as a state machine? Because it is one. And she's right. The problem is, there's a lot of states in that state machine, right? I mean, if, per gig of RAM alone, that's what? 2 to the 8 billion states that chunk of gig of RAM could be in. That's a lot of numbers. If you want to turn that into decimal, then the Windows calculator doesn't like you. I'm glad it didn't crash. So I mean, for reference, protons in the known universe is something like 2 to the 280th or something, and we're talking about 2 to the 8 billion, right? So if we want to fight this complexity of that, because that's kind of our day job, right? I mean, as computer scientists, we're here to fight complexity, and sadly, the complexity is of our own making, right? So we're kind of battling ourselves. So, in order for us to somehow reason about unit testability of code, then we need to drastically lower the number of states that we would expect that gigabyte of RAM to be in. Right? Sort of, I think the problem that I had coming into software design is, I had personal experience in small projects, and all these people that are asking me these questions, they have personal experience, right? They've done some toy projects at university, right? But these have sadly been small projects. And this is kind of an unsolvable problem. You can't actually calibrate someone's gut feeling about software without actually showing them real problems, because that's kind of where your gut feeling calibration comes from, right? And you can't say, okay, we're going to learn, we're going to work our way into this code base, and in third semester, I'm going to tell you what we should have learned, right? Because real software is huge, right? I mean, most projects are giant code bases, and so things that we see sort of in our personal project, like, the time it takes to refactor things, for example, time it takes to refactor things is very small when it's a pet project and can easily become man-decades on a large code base, right? Okay, maybe with tooling, if it's clean enough code base that tooling can understand the code base, but that's a big if, right? So our gut feeling about how to write software, let's just call this variable A. Well, how many people can see that variable, and how hard is it going to be to refactor that variable and whatnot, right? I mean, there's this, once I went through my entire driver and replaced all of the ints, because nothing is an int, with somethings, right? Protocol IDs, packet IDs, standard chrono time durations, blah de blah. I actually found that I needed to do some very, very large scale refactoring because I had made one false assumption. So I was essentially typing for about 3 days. And the git diff was something like 10,000 lines of code that I had touched before I compiled it again. And I got something like 40-ish compiler errors. And when fixing them, some of them were parts of bigger problems and indicators that I hadn't refactored something properly. And all in all, it was probably 100 bugs that I found at compile time. And the funny thing was, when that thing finally compiled again, all the unit tests passed, right? I mean, that's luck of the draw. That's probably not going to happen every time. But I found all the bugs at compile time in that case because I had offloaded all of this discipline into the compiler so that it could tell me about it, right? And the scary thing is, my unit test probably would have found 40 of those bugs. That leaves 60 to be found in physical testing. Probably find 10, 20 of those. Maybe in the field find 10 more. and the rest are for future generations. Right? I mean, that's the terrible thing about software development. If you are very good at fixing bugs and your team fixes a lot of bugs on a daily basis, that probably means there's a lot of bugs in the finished product, right? And if your team spends a lot of time writing code and fixing less bugs, that's actually an indicator that there's probably less bugs in the finished product. So we don't really have a sense of time and scale of things, right? But we also have very, very bad sort of gut feelings of collaboration, right? I mean, once I'm collaborating with someone, then I need to work in a very, very different way than I worked before. And we're still struggling with this in my company. And we went from a one nerd company, nerd plus a few other people to sell stuff and make things and whatnot, to an 8 nerd company. And I have had to apologize for a lot of things. And rightly so, right? And there's portions of the code base where if something goes wrong, it's still me, right? Because, I mean, not only did I, not document it well enough, or at all in some cases, that's actually, again, that's maybe a symptom of the problem, lack of documentation, right? Because a lot of the time, documenting things that are weird, documenting things that are not patterns that people are used to, if you will, is very hard. You have to explain entirely new concepts, right? I mean, if I were to try and document all the weird tricks that I did in assembler there, that would be books, right? And it would certainly be harder than it was to write the assembler in the first place, because I did weird things, right? I mean, we as an industry, there is an amazing amount of things that we do the same in all companies, right? We all use stacks, for example. I mean, this sounds probably stupid to a few people. Like, of course you use stacks. Well, that system, that didn't use a stack, right? It had interrupt service routines, and it had sort of a main thread, if you will, or the main execution. And the interrupt service routines could interrupt at any time, and they had their own set of variables that they could touch, right? There was kind of this variant of local state for every interrupt service routine, and since 2 can't run at the same time, and they always run to completion, then they can just touch this data. And this is a very different model, right? So if we're making sort of looking at parallels between this and physics, it's almost like we can change the law of physics between different projects, right? And I think this is something that on sort of for several reasons we overlook. The fact that it's hard to collaborate with people across nomenclature barriers, right? Across sort of framework barriers. I mean, if you add a Node.js programmer to your team and teach them C++ syntax, they're still going to program very, very, very differently than the rest of your team, right? Or maybe not, right? Actually, the code that we write at work actually has more to do with, a reactive event-based style of programming than probably most sort of normal software, or normal C++ anyway, right? And this is quite hard. I mean, this is one of the problems that I don't really have a solution to in software, is if you try and change the fundamental laws under which everything builds on, then there's this huge inertia gap of installed base of libraries, installed base of software that's already out there, and installed education in all developers, right? People don't know why they make assumptions about this being the right thing for this task, right? I mean, if you don't fundamentally understand what a lock is under the covers and what it actually does and why you can synchronize things with locks, then you'll be very surprised that you cannot use locks on a threading model that shares a stack, right? I mean, if you have different routines that can preempt each other, then, but they all need to share the same stack, then every routine that preempts another routine must at some point run to completion before it can switch back to that other routine because it's on its stack, right? And if that is the case, then encountering a locked lock is a deadlock, because what are you going to do, right? You can't switch back to whoever's holding the lock. He's down your stack and going to corrupt you by growing. Right? So this brings us to sort of very, very, very different models of programming, which is hard to collaborate on with people who come from different backgrounds. Right? On the other hand, I would very, very, very much argue that the model that people hack together, and maybe I'm being a little unfair to some of the geniuses of software, but the model that people hacked together before my birth, what are the chances that that's the right tool for the job for every job today? Right? We build everything on p-threads, essentially. Right? And I think with that, looking at time, we can open up to questions, and we'll pick up here after the break.
Open it is. Questions, please. I mean, I know you've had so many, you're just too shy to ask. You can cover your face and then raise the hand if you're too shy. And yes.
Yes.
Hi. Question, do you think that the education that we receive today at the university is the correct one, or that it should change?
That very much depends on the university. But I won't say which university this was. I feel very strongly about this problem, because I think, if you kind of understand your role in life to be generally useful, then you get a lot of bang for your buck by improving education, right? And I visited most of the universities in my region, of which there are actually quite a few, and they didn't really want to talk to me until I actually just went to one of their lectures and then told them all the things that were wrong about his lecture after his lecture. And then most of them did want to talk to me at that point, which, to their credit. But one of them was brutally honest. And I applaud him for his honesty, and he said, okay, I inherited this script, this method of teaching C++ from my predecessor, who wrote it 15 years ago. And the problem is, I know it's wrong and old and just not good, but I'm relatively new here at the university, and a lot of people want to have my head because I haven't brought in a lot of third-party money so far, because I don't like playing bullshit bingo. And so they're looking for a reason to get on my case, and as long as I don't change anything in this script that I inherited, no one can blame me. And this is a terrible, terrible, terrible thing, but on some level I can kind of understand the guy. What's the use in getting fired, right? So the problem is very, very much, most problems in the world can be described in terms of feedback loops, right? What is the feedback loop in that situation, right? If that guy does good, does he get a pat on the back? Well, if he's moderating, probably. But no, he probably doesn't. Probably nobody cares. If he does it job bad, well, that depends on how he does it bad. Can he blame someone, right? Academia, blamability is the largest feedback loop, right? If you can push the blame onto somebody else for something that's not going well, and if you can take the credit for something that you probably didn't do. I know this is very, very dark, and there are many people in an academia who are amazing. I think Voter might be in the room somewhere. There's a reason why I try to get interns that he taught, right? He teaches in the Netherlands at a university, and he teaches very, very well. There's not a lot of people that teach anything embedded related in Western Europe, right? Probably in Germany, the best school is the RWTH Aachen, from Aachen. And they don't crank out sort of world-class embedded developers because they teach it. They just have a very good robotics club, which they keep finding smaller and smaller rooms to host it, right? And they have they don't understand that this is why, one of the reasons why they're very highly viewed. But that's the reality. I mean, I think, there are a lot of students in the audience. There are some things that university is very, very good at teaching you, and I applaud them for it. But there are some things that aren't, because there's a missing feedback loop. And to be honest, I don't just see the problem at university, because where does that feedback loop need to originate from? It needs to originate from industry, right? I mean, that's where the rubber meets the road. That's where we have sort of a Darwinistic race to a better product or a better solution. And there's not a lot of collaboration between industry and universities. I mean, it seems like in many cases there's this feeling of, yeah, those people at the university don't know anything, unless it's self-driving cars, in which case we're just going to do everything they tell us to, right? I mean, there's a very sort of schizophrenic view of university, and there's not a lot of collaboration beyond send me students. We have a hiring problem. I mean, essentially every software company has a hiring problem. Actually, probably another lesson to you young people: shop around. You're valuable.
Any more questions? Okay, one over there.
Actually, I have two questions.
Yeah.
I wanted to ask: is there? Have you figured out any way of training yourself or your brain in these terms of when we have different backgrounds? For example, what I was thinking about, like, if you are writing in imperative or functional programming languages, there's a different approach. So
Yes.
so this way you can slightly, well, change your way of thinking. Are there any other ways you would recommend or advise how this this bias we have from our experience can be somehow aligned or fixed? Or
Yeah, I would very much recommend when you're young and have time to do these things. I mean, as soon as you have kids, you don't have time anymore. I mean, 10 of 10 would father again, but yes. And maybe other things in your life, you don't have much more time to play around with things. When you're young, I would certainly look at a functional programming language, an event-based framework, maybe an alternative kernel, some things that are not just your run-of-the-mill software development. And I would say in general, you guys familiar with the 80-20 rule? Don't burn out on anything. There's going to be a better way to do it, right? I mean, if you actually have to give 110% for a long period of time on something and you don't feel like you're making progress, take a step back and try and increase your level of abstraction, or change the paradigm, or find another way to do this better. Because once you get close to that 100% and you're not making progress, you're doing it wrong, right? I mean, I think this is probably, the number one reason for burnout in software is, people are increasing the law of diminishing returns, and they don't look for other options, right? I mean, looking at my own life, sometimes I've worked 90-hour weeks, sometimes I've worked 35-hour weeks, sometimes I've had weeks where I just did projects that were fun, right? And my personal sort of stress level that I've felt has not mapped to the number of hours I've worked very well, which I think is a good thing, which means that at least in the second half of my career, when I find that I don't have the right tools for something, I don't try and brute force it with man hours. But I certainly, I'm not sure if I've quite answered your question completely. I think in the second half of the talk, I am going to go into sort of learning how to write software in a way that what our brains have evolved to be actually understand, actually works better, and sort of observations on that, and a few concrete examples. So I hope to answer your question throughout the second half of the talk, and ask it again if I haven't.
okay,
Yeah, he had a second part question.
Just
Yeah.
the second one. Yeah, I was wondering, have you maybe noticed some patterns? Like, because at the beginning you mentioned, at the very beginning you mentioned that people sometimes don't understand high-level concept because they have some lack of knowledge in the low-level thing. And I was wondering, have you noticed, like, is there any, like, can you say, like, people these days don't understand something, and that's why we have a problem of something else? Like,
I'm not sure it's really one specific thing. I think it is probably different for different people. Actually, Sean Parent here in the front row has a very good example of this, where he, was kind of poking fun at his son with and a computer science degree and didn't know how to build an AND gate, right? And the punchline of this is that later, Donald Knuth mentioned that he couldn't do that either. And I hope I'm giving this correctly, at least in sort of a dumbed down abstraction, right? And so people arrive at their skill, sometimes the same skill, from different angles with different sets of fundamentals that they understand. And it's actually not really a question of arriving at the same skill, right? I mean, my generation and your generation, as in you're all mostly younger than me, the number of people who have graduated university in these two generations is more than have graduated university since the dawn of time, right? I mean, this is not seldom anymore, but the number of problems to work on has also increased, right? So we have a lot of people with the, essentially very similar sets of knowledge, but these sets of knowledge are a subset of all knowledge, right? And so unique knowledge is very, very valuable in that system, right? I mean, the amount of things that university is good at teaching you is constrained because of another feedback loop, in my opinion, right? I mean, a lot of people that teach at university, their previous profession was student, right? So if something was missing in their education, it's probably missing at 10 universities in the next generation, right? And Feynman, for example, is a very good counterexample of this. He was in industry and then came back to university, and that's probably why America won the Cold War, because their physics was better, because Feynman came back and taught everybody how to think about things.
As a former university teacher, can I have a question?
Yes.
So what's the difference between assembler and compiler? Then they sound the same to me. No, scratch that, actually. But I do have a question for the audience. Could you please come back in half an hour? Because if you do go away, then there'll be new people coming in, and then I'll have to introduce Odin again, and I really don't know how to do it anymore. So please do show up in half an hour, and then we'll take the second part and some more questions. So 3:30, please.